Today we start learning about the basic circuits of the analog IC chip. We talk about how to design IC chip. Analog circuit designer, they have designers who can design PCB board using analog IC chip like operational amplifiers, voltage regulators, and other discrete component, transistors, diodes and stuff. And they are mainly designing like audio equipment, measurement equipment, the control circuit, and also high-speed analog circuit on the PCB board. Here we learn how to make analog chip itself, and the very basic stuff on the chip design. The first, you have to know how to make analog to the analog constant voltage and current. And if you don't know this, you cannot design analog IC chip. So the very famous basic circuit we are going to explain here, and that's the first step to be the analog circuit chip designer. What is constant? The constant against what? Analog chip has a VCC, typically plus 5 or 12 volts, sometimes different, and the ground. And this VCC has a plus minus 5 volt or sometimes plus minus 10 volt variation. And internal circuit provide the constant voltage from ground. This voltage dt dVCC is 0. That's what it means, constant voltage. Have a constant current source. You have a current source, and this current source dVCC is also 0. So even you have a power voltage variation, the current or voltage constant cannot change. That's a constant. And another important thing is constant against also temperature. Basically, bipolar transistor, VBE and IC has a relationship. What kind of relationship? Okay, this is a typical for same ICC, you maintain same VBE, but temperature change, VBE change. So when temperature goes high, VBE get less. So what's happened is, if you have a circuit like this and you provide a constant voltage, but this cannot be say constant voltage provided emitter, right? Then this is constant current. Previous digital circuit, we introduced the emitter coupled logic, and that has a constant current like that. And this cannot be constant against the temperature, because when temperature goes up, this VBE gets smaller. Then the voltage between across the voltage resistors increase slightly, the current increase. So this cannot be constant current against the temperature. Okay, so in this graph, if you have this kind of configuration, this move like that, when temperature change from T3 to T1, the IC current slightly more, but VBE is still less. Okay, so the constant voltage doesn't mean constant current can be provided easily. Also, the current mirror circuit, when you have I constant current, the mirror side is also affected by same temperatures. Okay, now you know IC equals I0 E and VBE over VT. This VT is a thermal voltage, KT, Boltzmann constant temperature over Q, and it's about 26 millivolt. Okay, now here's the important things. So VVE in this equation is going to be VT log VV IC over I0, right? And this VT is KT over Q. So this looks like DT is positive. That's strange. We just saw this. The VVE decrease as temperature goes up. It's negative. Okay? And a lot of people confused about this, because simply here's the very good article from Toshiba about this problem. Why this equation shows positive, but VVE has negative temperature coefficient. D is negative. Why? The reason is this I0 is also strong function of temperature. So I0 is typically Ix. Ix is the current at the fixed temperature. KT means I0 increase exponentially by the temperature. So if you plug in there, let's see, VVE equals VT log IC over Ix. This time it is constant, and minus KT. So if you take derivatives, then it's approximately the K over Q log minus IC over Ix minus K, and dVE dt. Okay, so what happened is this derivative is it's an approximate derivative. You have to take a derivative on the both side and clean up the equation, but this becomes somewhere around minus 2 millivolt per degree. Okay, so remember VVE has a negative coefficient over temperature variance. This is about the value, and more details explained here in Toshiba's paper, and if you're interested, you can read through this. So one thing you have to remember in the analog design, VVE is a log function of IC, and also VVE temperature coefficient is negative around 2 millivolt. degree. Okay, and these are the one we need to use as a parameter to design the very basic constant voltage. And once we get the constant voltage, we can design constant current. This is the VBE, and this is R. And but this, if this is constant voltage, means it's constant against the VCC and temperature, this I is going to be, it's constant against the VCC but not temperature, because VBE change here. Okay, so you have to understand this. The most of ECL circuit, digital circuit, use this type of constant current. So it's not temperature compensated, but somewhat compensated actually, because this resistor value increases as temperature goes up. Okay, but it's not fully compensated. Okay, so this is a very famous circuit to get a constant we use a transistor, the same as diode, right? And what you do is you have another transistor and another transistor. We give a negative feedback by this connector. Okay, so this is called band gap. Voltage supply. So what it is here you can have any VCC. You change VCC around, this going to be pretty constant. And also this also very if you adjust this parameter correctly, R1, R2, R3, and the size of transistor, then this is also, we can make it temperature compensated. So this circuit is used all over in every analog IC chip and also some of digital circuit. We have to understand this design, and that's what I'm going to talk about, is so that you can get a good idea of analog design. Okay, now here what we do is we kind of set parameter I1, I2, and I3. This doesn't matter, I3. This voltage VBE, we kind of adjust so that it's going to be same as this VBE. That means base collector voltage is almost zero. Okay, and the current I1, I2 is same. Okay, so what we can do is we make the reference, this voltage is VBE, right, plus this voltage, and this voltage is amplifier. This is amplifier. It's typically R3 over R2 of this delta VBE. Delta VBE. And what is this delta VBE? It's the same current. How come this has the delta VBE? Well, the size of transistor is different. Say Q2 is 10 times larger than Q1. So current density will be much less. So we talk about current density of this transistor J1 and J2. So delta VBE is actually let's see, VT J1 minus J2. This current density and this current density, this is going to be the V delta VBE, right? Okay. So this equation is completely free from VCC inference, right? It doesn't matter what the VCC say, plus minus 10 volt change. This guy stays same because it's determined only by this current density and the ratio and the VBE. And this current density ratio is going to be pretty much same because we keep this voltage same. How do we do that? We look at the equation and adjust R1, R2, R3 such a way this becomes same. So this won't change by VCC. This is completely dVref VCC is 0. Okay. So now next one is how we make it temperature independent. So dVref dt is 0. That means dVBE dt, right, is going to be R3, R2, J1, J2. Okay. Now, J1 and J2, they actually said this Q2 is 10 times larger, say n times larger, right? So J1 is proportional to say this is a unit. So this is like a n times larger. So I2 divided by n and I1. So it's going to be ratio of I1 over I2 divided by n. We can put the n here. So it's going to be n I1 I2. Okay. So this we know this is going to be like a minus 2 millivolt per degree. So this I1 I2 we make it I1 I2 same, and so let's see. R1 I1 equals R2 I2 equals the voltage E. This is the voltage, drop voltage. on this circuit, this drop circuit. So we put I1 add I2, it's going to be R1 R2. Yep. So we adjust R1, R2, R3 to be about negative 2 millivolt. Okay, then it's temperature compensated. So how we do that? We had to do some kind of try and error. So somewhere around the, say, V reference is about 1.3 volt, and the VVE is 6 volt. So R2 voltage drop cross R2 is 0.7 volt, and suppose we choose that 1 milliamp, right? And N is 10 times larger. So we choose about 700 1 millivolt, 700 so 700 ohm, and this transistor is 10 times bigger, right? And say this transistor is same size as this one, Vref. Okay, so we have to determine R2, R1, R2. You can go through this exercise and try to adjust to be negative 2 millivolt. Then you're done. Then you get VCC, temperature compensated, constant voltage. Remember, this circuit you have to go through many times and memorize it, because this is the most basic analog circuit you use on the analog chip design, the constant voltage generator. Okay, and using this we can create a constant current source, and we can compensate on temperature. So there are many ways to do it. And also then Vref has to be around 1.3 volt. No, once you have a constant voltage, then you can create many other different voltage from here. And since this is compensated already, it's constant against the VCC, and make it temperature compensation is very difficult for various cases. Each case you have to evaluate and make sure temperature compensated. But if temperature compensation is not critical in analog design, then at least you know how to make VCC compensated any voltage, any constant voltage. For example, you can stack up the diode on top of this and you need some kind of feedback loop. From here, actually you don't connect this. You go up and make it output transistor. This is the output. And you divide this voltage to the ratio you want and give a feedback to this guy. Okay. So something like this kind of circuit is going to create different voltage. Way higher than this, like 1, 2, 3. You stack up 3 times, and this ratio the output, the feedback goes to this ratio. Okay, so you analyze this circuit, you can get the 4 VBE higher constant voltage. It's compensated against the VCC. Okay. Another method, the cheapest method, is to use Zener diode. You have a Zener diode and current flowing, and this provide certain voltage. It's rather this way. So this voltage depends on Zener diode. If it's 3 volt, you can get 3. Okay. But in order to have a fan out, usually you use emitter output for this one. So Zener diode, you can combine this with this. Instead of here, we put the Zener diode here. Okay. So there are many different ways to design the constant voltage and the constant current in analog circuit. Okay. Okay, this is a very important circuit, so you have to memorize this, and you should be able to create any constant voltage at any time within the analog IC chip. Okay, that's it. Let's if you like this, please subscribe, and let's get on to the hand-on electronics. Today is a hand-on electronics. Actually, there's no way I can test the VCC variation and temperature variation on my breadboard, so we're not going to make that. Instead, we explain to you what you need from now on. In the beginning, I suggested that you can get really cheap one, like this $10 power supply, the 5-volt power supply for this breadboard. But the problem is, when you make a mistake, for example, there is stupid one wire is crossed from VCC to ground and short circuit, then this busted already. Every power supply should have some kind of voltage protection means when overload protection means when short circuit happens, it's immediately shut down the output and protect the equipment. But this kind of $10 stuff doesn't have sufficient protection, so it's gone already. It's already bad. Okay, so you need a breadboard, and what you need is instead better power supply. It's about $60. I show you. How to move. Let me move the camera. 5 voltage supply, and this has the sufficient protection. I tested. I overshot short circuit, and what's happened is it's dropped, voltage immediately dropped, and short circuit it burned a little here. You see it, a little dot, but voltage supply is never get damaged. It's got sufficient current supply too. This one can supply up to 50 amp, so it's never go busted. Okay, so what you do is you need this voltmeter, and it's convenient to check the resistor values and the voltage, DC, AC, anything. This kind of digital type is very convenient. And you need oscilloscope. I got a little bit better one. In the beginning, I said we can use this cheap one, like $50, but there is a limitation. So pretty soon, I thought it's necessary about $200 oscilloscope. So this oscilloscope is going to help me to demonstrate the hand-on electronics from now on. Okay, so that's all I have. And so it's very small, tiny. The lab bench here has a lot of used parts and plenty of wire to connect. Okay, and that's what you need to do the hand-on electronics. You can create any kind of circuit. And the IC chip, we're going to bring in a lot of IC chip. You can buy IC chip online, very cheap. It's not gonna be more than a couple dollars, and you can do plenty of experiment with the LED, the lights on and off. If you are in the programming, then you can get the little microprocessors and start programming on the breadboard. Okay, so that's what all I have today, because this constant voltage, constant current is very hard to do experiment. It's need more equipment to do that. So I'm not going to build, for example, like a 10 large transistor. You need to put the 10 transistor in parallel, and that's pretty difficult to do. IC chip design, it's very easy. Just scale the geometry, then you get 10 times bigger transistors. Okay, so that's a difference. And we get into other type of analog electronics too, using op-amp and some analog chip. Using chip, make some analog circuit. Not only the designing chip itself, but using chip, you can design analog circuit, and we are going to get into that. Okay. If you like this program, please subscribe and continue watching to polish up your electronics skill. Electronics is you can learn from book, but the book alone is kind of boring, and sometimes you really don't know the the reality of electronics. There are a lot of problem happens, like some oscilloscope pick up noise. You have to find out where the noise is from, and somehow according to diagram is supposed to have certain voltage, but it's totally different voltage and kind of things. And it's sometimes parts is bad. Hand-on electronics is a real world troubleshooting. It's different from learning electronics on a piece of paper. Okay, so thank you for listening, and next one is the analog circuit again. See you.